Welcome to the AI for Technical Writers podcast, where we help you get smarter than your competition. This is episode 113. I'm Fred, and joining me as always is Daphne.
It's great to be here. Today, we're looking at something really exciting, I think, especially for anyone who has to, document or explain AI systems.
Right.
We're focusing on a potential solution to that old AI trade-off.
The classic documentation headache. You get accuracy or you get transparency, but good luck getting both. For years, we've had this choice, haven't we? Explain a simple model that frankly doesn't work that well, or just sort of wave hands at the output of a powerful black box.
Exactly. So the focus today is a new classification approach. It's designed for interpretability right from the start. It's called the Geometric Mixture Classifier, or GMC.
DMC. Oh, before we dive into the mechanics of it, maybe let's credit our sources.
Good idea. Yeah, this analysis was actually suggested by our producer, Curt Robbins, who's a senior technical writer himself. He flagged this as really important for people in our field.
Makes sense.
So we looked at the article, A Model with Many Minds, Exploring Geometric Mixture Classifiers. It's by Diana Wolf T., published October 30th, 2025.
Got it.
And that article discusses the GMC, which was developed by Shubham Sharma. He founded Sonitech AI and co-authored in a paper with Prasanth Rawal.
Okay, so our mission then is to figure out how this GMC thing offers that middle ground. How can we get accurate predictions for complex real-world stuff, but still be able to actually explain how the AI made its decision? Let's start with why the traditional methods often fall short.
Right. Well, the main problem is something called multimodality. Basically, the categories or classes that we try to classify in the real world, they aren't neat little blobs. They're messy.
Messy how?
They overlap, and crucially, they often split into different subgroups within the same category.
Okay, subgroups within a category. The source had that cat metaphor, right? Which I thought was pretty helpful.
Yeah, the loafers and pouncers.
Yeah.
If you're just trying to classify cat, you might miss that there are these really distinct behavior clusters inside that label.
So, like, the loafers are maybe defined by low activity, sitting still.
Right, round shape, that sort of thing. And the pouncers. They're all about sudden movements, sharp angles, high energy.
And traditional models, especially the simple linear ones, they try to draw just one single line or boundary around all the cats.
Exactly. One global rule for everything. But that forces wildly different behaviors under the same umbrella, and, well, it doesn't work very well for telling them apart accurately.
So things like logistic regression or standard SVMs, they just can't handle that scattered, multimodal structure because they're stuck with that one flat boundary, one hyperplane per class.
Precisely. They just lack the expressivity needed, which is why people usually jump to the heavy hitters, right? Kernel SVMs or deep neural networks.
The big guns.
Yeah.
And those nonlinear models can handle the complexity. They can sort of weave around the scattered data points. But there's always a catch.
A big catch, especially for us.
Right, the price. And it's steep. First, you lose interpretability, total black box. Second, they need tons of tuning.
Lots of fiddling.
And third, the computational cost is often huge. You need powerful hardware. That trade-off, performance versus transparency, it's the reason documenting AI failures can be such a nightmare.
And that need for transparency, especially out in industry, that's actually key to where GMC came from.
Oh yeah, the inventor's background. Sharma wasn't just an academic, right? He started in petroleum engineering. Aker Hughes.
That's right. He encountered machine learning trying to optimize these complex real-world industrial systems.
And in that world, you can't just deploy a black box.
No way. If something goes wrong with $1 million piece of equipment, you need to know why, fast. Debugging has to be possible. Trust is essential. GMC really grew out of that practical need.
Okay, so GMC tackles this multimodality by giving each class a team of internal experts.
That's a great way to put it. Instead of one rule for all cats, it allows separate simple rules for the loafers and for the pouncers within the cat class.
So it acknowledges the subgroups.
Exactly. It models each class not as one thing, but as a mixture of multiple simpler structures. Technically, it's a mixture of multiple linear hyperplanes.
Okay, linear hyperplanes. Let's pause there. Why is sticking with linear important for transparency, even if you mix them?
Because a single linear hyperplane is fundamentally simple. It's just a flat decision surface. You can always trace it back to a clear rule.
Like in a Theothan statement.
Pretty much. Like, if feature X is above this value and feature Y is below that value, then it's likely this class. It's understandable.
Which is totally lost in a deep network with millions of parameters interacting in complex, nonlinear ways. You can't point to one reason easily.
Not easily at all. So GMC uses these simple traceable rules, these hyperplanes or mini-experts, to define different parts of the class structure. It's like drawing small, clear property lines within a neighborhood instead of one giant, messy boundary around the whole city.
Okay, that makes the geometry understandable. But if you have, say, 10 mini-experts for one class, how do they decide which one makes the final call? Does that part become a black box?
Good question. And that's where another key part comes in. It uses something called log-sum expect pooling. It's not just a simple vote.
Log some expect pooling.
Okay.
What does that do?
Think of it like a weighted consensus. For any given data point, some of those mini-experts, the hyperplanes, will be very confident it belongs to their region, others less so.
Right.
Log-sum X pooling gives more weight to the confident voices. The strongest, most relevant expert essentially gets the loudest say in the final decision, but the others still contribute softly. It avoids letting a weak guess take over, but it also avoids complex aggregation methods that would hide the reasoning again.
So the decision is still traceable back to the winning simple rule,
Mm.
the hyperplane that was most confident.
Exactly. You know which mini-expert drove the decision.
That's huge for documentation. If I can point to that specific rule, I can write a test for it. I can explain the failure if it happens.
Absolutely. That comprehensible geometry is the key. It avoids the opacity of deep learning while still capturing complex patterns.
Very interesting. Okay, let's take a brief break for a special message from producer Curt Robbins.
Hi, this is Curt Robbins. First, thanks for listening. I truly appreciate your support. I want to let you know that I'm currently accepting new clients. My rates are affordable, and I have more than 25 years of experience working for enterprise companies like Microsoft, Northrop Grumman, Oracle, PNC Bank, FedEx, USAA, and Wells Fargo, among many others. If you want to improve your IT documentation and communications, hire me. I deliver fast, know how to use AI to improve efficiency and accuracy, and love going the extra mile to satisfy my clients. Thank you for subscribing and listening. Back to you, Daphne and Fred.
Welcome back to the AI for Technical Writers podcast.
All right, before the break, we were getting into the mechanics of the geometric mixture classifier, how it uses multiple simple rules, these hyperplanes, and that log sum X pooling to stay interpretable. Now, let's really focus on the payoff. Why should technical writers and IT folks care about this? What are the practical wins?
Okay, 3 big ones, I think. First, as we touched on, understandable decisions and traceability. Because you can link the output directly back to a specific simple hyperplane. You know which subrule or mini-expert was most responsible.
Which, for auditing or compliance, is just gold.
Totally. It changes how you document things. Instead of just saying, here's the input, here's the output, the model is complex, you can actually document the reasoning path for specific predictions.
Right. And if it makes a mistake, say, misclassifies a transaction, you can potentially isolate which rule messed up and adjust just that part instead of retraining the whole monster model from scratch.
Exactly. Okay, second big win. Trustworthy confidence, or calibration. We know lots of complex models can be wildly overconfident.
Oh, yeah. It says 99% certain, gets it wrong half the time. Dangerous stuff and impossible to document reliably. You can't put guarantees in a manual based on fake confidence.
Well, GMC, because of its structure, allows for a relatively simple calibration step. This means its reported confidence scores actually line up pretty closely with how often it's right in the real world.
So the confidence score actually means something.
It's much more reliable, which is critical if you're deploying this in high-stakes situations. You need the model to be honest about its uncertainty.
Okay, traceability, reliable confidence. What's the third? Efficiency. I mean, if you're using a mixture of hyperplanes, isn't that like running multiple models?
Yeah.
How is that lightweight?
That's a fair point. But the efficiency comes from what kind of computation it's doing compared to, say, deep learning. Deep networks involve these huge matrix multiplications, very dense computations.
Right.
GMC still uses matrix math, but the operations are simpler. And there are just far fewer parameters, fewer moving parts overall compared to those deep models. So it trains faster, uses less compute power, and can often run on standard hardware.
Ah, okay. So you get the ability to model complex data, like nonlinear models, but without the crushing computational overhead and hardware demands.
Pretty much, yeah.
And that deployability, that efficiency combined with the transparency, that really matters in those high-stakes areas we mentioned. like medical diagnosis.
Definitely. Think about diagnosing cancers or diseases. It's often not just cancer YN. It might be specific subtypes or early versus late onset.
Different substructures within the main class.
Exactly. A model like GMC can potentially identify those different facets and tell the doctor which specific pattern or subtype rule was triggered for that patient. Same goes for fraud detection or financial risk, and you need to know the kind of risk, not just that risk exists.
Okay, so it sounds great in theory, transparent, traceable, calibrated, efficient. But did it actually perform well? Did it keep up with the established models?
Yeah, and that's the really impressive part. The paper shows results from standard tests, UCI benchmark data sets, those tricky spiral data examples that trip up linear models. And GMC performed comparably, sometimes even better than, models like random forests, standard SVMs, and neural networks. And it did that while remaining inherently interpretable.
Wow. Okay, so it really delivers on that promise.
It seems to. It really supports Sharma's core idea, finding that middle ground where you don't have to choose between accuracy and transparency. It kind of blends the clarity of linear models with the power of nonlinear ones.
Which, going back to documentation, is a potential game changer.
And importantly, this isn't just theory. The researchers want people to use it. The actionable thing here is that the code is actually available.
Oh, really?
Yeah, it's in a GitHub repo linked in the paper. They're encouraging the research community and practitioners to try it out, adopt it, maybe even extend it to more complex data.
That's great. A practical tool, not just an idea. And it really makes you think, imagine if all AI models had this kind of geometric interpretability built in. How much easier would our jobs be? Writing documentation you could actually stand behind because you could explain the why. That shift from documenting opacity to documenting transparent geometry, that would fundamentally change technical communication in AI.
Thank you for listening to the AI for Technical Writers podcast from Curt Robbins, where we help you get smarter than your competition. Remember to like, subscribe, comment, and share. We'll see you next week.